So we're going to look at a pretty straightforward measurement of the speed of sound today. What we're going to do is just have a sound source emitting some sound waves and connect it to a microphone and another microphone with some space between them that we can measure. And then we'll look at the time between the signal arriving at the first and the second microphone. And for a quick look at our setup, I've got a microphone mounted on a stand here, another one over there, and both of them are wired to this audio mixer that I'm using to just amplify the signals and so that I can look at them on this oscilloscope. I've got a laser distance meter here at one of the microphones, and I'm just going to measure the distance to the other microphone, lining up the laser like that. So now to collect some data for this experiment, all I have to do is stand behind the microphone, emit some sound. I'm just going to clap my hands together, and as long as I'm sort of along the straight line connecting these, then the sound will reach this one. Some delta t later it'll reach this one. I use the laser to measure delta x, and then looking at the signals on the oscilloscope screen, I can compare the time of arrival. So here, there's a few important things to note. The signals do look a little different. This is the first microphone and this is the second one. You can see the second one, the signal arrives later in time, but they're also shaped a little different too, and that's just because of the sound bouncing off different surfaces around the room. The sound of my hand clap sounds different at the first microphone than it does at the second one. So looking at these here, I would kind of make a rough estimate that they're offset by maybe 1.5 squares or divisions. And down here at the bottom, it says M 2.5 milliseconds. That's the time per division. So if this one arrives, or sorry, 1.5, did I say 2.5? Anyway, it's 2.5 milliseconds per division, and this signal arrives 1.5 divisions later. So the delta t here is 2.5 milliseconds per division times 1.5 divisions, which would give me 3.75 milliseconds. If I line up the cursors with this one, we'll take this first little peak of the signal because that's easy to see when that is, and line up the other cursor with the other peak here. It's giving me exactly 4 milliseconds. So that was pretty close to my sort of quick estimate of 3.75 milliseconds, but using the cursors is a more careful way to compare the time offset between those, as long as we use features that we're pretty convinced match up. So what I'm going to do next is run the experiment a few times, get some delta x's. I'll take pictures of the oscilloscope so that we can get some delta t's, and then we'll have some data to work with. And just for comparing to what we expect the speed of sound to be, looks like the temperature in here today is a little bit above 25 degrees C. I've got a 25.7, 25.3, and 25.5 for an average of 25.5.